So let's talk a bit about the forces that are driving this energy transition itself. And so I have four listed there. You may find more. But the notion is the first starts with decarbonization, right? So we want more clean energy sources. And so many of those are renewables, whether it be wind, whether it be solar. There's also hydro. That's a form of renewable capability we have. And many companies are now stating their carbon neutrality. I will be carbon neutral by 2030, 2040, 2050 to certain degrees. And so that's a massive force motivating us. Second is this notion of electrification. Now, while decarbonization and renewables growth is talking about the different sources of energy that will be created, electrification is all about the sinks, where that electricity goes to, people who use it. And so we see a significant rise in the electric vehicles, electrified homes using heat pumps, a number of other things that are going to be using or sources of that electrical growth. Then there's this notion of decentralization. What that refers to, normally we have centralized power generation. You have these large combined cycle plants, large coal plants, large nuclear plants, and it's all sent from a transmission to a distribution grid to consumers, people who use it. However, right now in the distribution grid, you have people who are also generating their power and consuming power. Think about residential homes with solar panels on the roof. Think about industrial sites that are now adding wind farms and are adding batteries so that they can actually become more green, because they too have carbon neutrality targets. They can not only use electricity, but they can generate it as well. So that's a decentralization. And that's all these microgrids, virtual power plants, distributed energy resources. And finally, another massive market force is this notion of digitization. We have many more devices and sensors connected so we can get the state. Now, when you think about all of these things, think about the underlying sort of mechanics. There's a lot of dynamics in the system. So there's dynamics in that you're adding renewable sources, and renewable sources, are based upon the wind and the sun, which can vary. There's a lot of dynamics there. There's dynamics in electrification because people are adding new electrical vehicles. They're putting on solar panels on their roofs. Companies are adding wind farms to give themselves, more green power. So there's dynamics as these things get added there. There's the dynamics in decentralization, because not only on the distribution grid can I actually use electricity, but I can generate it. So at any given point in time, I could be handing back to the grid. That's a dynamic. Then there's dynamics even in the digitization, because again, there's cyber concerns that you have. So there may be situations in which through malfeasance or mistakes that these things go down. Then I can add on top of that dynamics with the weather. So there's a lot of dynamics, and that dynamics is running on a base that is extremely stable. And when I say that, I'm thinking about if you look at these combined cycle plants, these gas turbines, they have a life of about 35 years. Wind turbines, 25 years. Many of the grid hardware pieces have been around for 30, 40 years. So imagine all of those dynamics on top of something that's extremely, constrained. And not only is it constrained physically, but it's also constrained with a number of government regulations as well as a number of financial commitments. So in the face of those dynamics and constraints, you have to find a way to deal with that, and a perfect environment for the digital twin to actually handle the complexity of the situation with the dynamics and find ways to give you an insight into early warning of problems, understand what we could predict, and understand what we could optimize. And why I think about this all the time is because I'm part of GE. And in GE, we live in this world. 1/3 of the world's electricity is generated in some form or fashion by our generators. We also have grid software in which 30% of the electrons on the planet flow through that software. So we see this in spades. So if you think about those dynamic forces in this constrained environment, how do you think of business value? So what you look at is, what are the ways you can use a twin to deliver value? And there are really three things we think about. Can I get early warning on a problem such that I can take an action so that I don't have, significant adverse consequences? Can I either predict the remaining life on a part or a component on a system, or predict a drop or a potential opportunity to increase performance? And then can I actually do some form of optimization? Can I optimize so that I can have the lowest cost electricity with the lowest carbon that's the most stable? So those are the things we use digital twins for. So let's talk about sufficient early warning. What we're doing here is we have a hydro plant, and in the hydro plant, we're trying to figure out when there will be cavitation. You know, the air bubbles that collect, these things cause vibrations. Vibrations damage the bearings. So how could we build a twin, which is what we've built, using some of the design knowledge, manufacturing, and servicing knowledge, and then combining that with a significant amount of time series and other data to actually give me an anomaly score to alert me to when, you know, I should be seeing, I'm getting early warning on a problem that could be vibrations that would damage the bearings. And you can see here, you know, we can talk about how much, if you can do that early detection, that we can estimate that's a 100K savings. Second is life prediction. How can I look at a combined cycle gas plant? Because I'm using these things. These things were built and meant to be turned on and operating at the optimal maximum capacity. But now that you've added renewables, right, and renewables are variable. Some days the wind blows, some days the sun doesn't shine as much. You have these combined cycle plants now operating in a cycling fashion. They're not always on, they're not always off. So that causes damages to the parts. How do I maximize my profit while minimizing the damage to the parts? So I've got to predict the damage on the parts as I cycle these things up and down. In performance prediction, the wind is extremely dynamic. A wind turbine stands 300 feet in the air, and each foot from the ground, the wind speed is different. The wind speed is different at different times of the day, each hour in the day, different times of the year, different based on weather. How do I understand that wind that's blowing and then alter the pitch and the yaw of the turbine itself so I can have the maximum energy created? And finally, the grid itself. How do I forecast the potential generation based upon renewable sources and the demand and balance it in such a way that I can get the best energy at lower cost, trying to buy that energy a day ahead, and then in some cases, maybe 15 minutes ahead. So these are the ways you actually extract value.